At the HCES Engineers Week Banquet in Honolulu in February 2024, Meech presented this keynote address on the construction of a habitable world. Meech is an astronomer/astrobiologist at the University of Hawaii's Institute for Astronomy and investigates how habitable worlds form. She uses the power of interdisciplinary science to address fundamental questions about how Earth got its water. Karen is a past TED Talk presenter. Earth's water is key to the formation of life on our habitable world. Is it unique? Looking at the construction or formation of our solar system likely holds the answer. Based on years of interstellar observations, space missions, and geology, she tells the possible story of the source or sources of Earth's water and the role the formation of our unique solar system may have had. Using the ocean's chemical fingerprint, the ratio of deuterium to hydrogen, she explained the various possible four sources of water: comets, hydrated meteorites, solar nebula gases, or chemical reactions on Earth. Her story's journey ranges from Hawaii's and Chile's telescopes, to geology on Iceland, to our solar system's gas giant planets, space missions to Halley's Comet, and to the furthest star-forming galaxies in the search for the source of Earth's water.
Thank you very much for that nice welcome. So that leaves me, 2 minutes left? I wasn't sure if I was going to like being a keynote speaker, because I've been to so many events where there's a keynote speaker and you're just starting to fall asleep, so I have to make this interesting. Since this is an engineering society, I had to have something about engineering in the title, so you may think it's strange, but I put constructing a habitable world. I'll start with a little bit of humor. When I was putting this talk together, I remembered something that happened to me in 1996. I received this letter. The point is, you shouldn't be able to read the text, but it's all in French. I don't speak French, so I went to my brand new postdoc and I said, "Help, what is this?" He goes, "Oh wow, this is really prestigious. It's an invitation from the French Engineering Society to give a lecture at the Sorbonne. They want you to talk for 2 hours on the industrial application of comets for 700 people. And it must be in French." I said, "I don't speak French." He said, "Don't worry, write out your slides, I'll translate it, and you can read your lecture." So I started to fret about this and worry, how am I going to talk about the industrial application of comets? And finally, he burst out laughing and said, "It's a joke, it's a joke." So that postmark, he manufactured by hand. But I had actually been invited to give a talk at a mining engineering meeting in Canada, and I did give a talk there. You can ask me about that later. But what we're going to talk about today is really building a habitable world in a solar system. How do you make a solar system that can support life? And in fact, people joke, your field is astrobiology, but it's a field with no content because we haven't found any life yet. But it's really about understanding how you build a planet that could support life. And in fact, what you would really like to do as an astronomer is observe the process. We can't quite do that yet. That beautiful picture in the upper right is a picture taken with a telescope shown at the top. This is a sub-millimeter telescope in Chile. It's resolving an image of a young solar system being born. But the scale isn't quite right to watch something like Earth being born. The scale there, astronomical units, 235 astronomical units across. Earth is 1 astronomical unit from the sun. So we're starting to see solar system construction, but not planets that are of interest to us. But we're thinking that by the 2030s, we will be able to resolve solar systems and look in at the heart where we think the planets might be. And I think this is important because as of today, there's over 5,000 extrasolar planets known, maybe 10,000 more candidates, and of these, maybe at least 50 are habitable. And this beautiful picture at the bottom is of the TRAPPIST-7 system, which has 7 rocky planets very close to the star, 3 of which might actually be habitable. Now, this is important because we only know of 1 solar system that's habitable and inhabited, and that's us. So we really need to understand how our solar system formed. And in fact, if you look at that picture of TRAPPIST, you've got all these rocky worlds smashed really close to the star. That looks very different from our solar system, which has rocky planets, fairly close to the star, and outside of that we have the gas giants. And one rocky planet Earth is at just the right distance for liquid water. But that's not the way other solar systems are built, and this is just a diagram showing a few hundred planetary systems, and what's plotted across the bottom is how long it takes to orbit the star, and across the y-axis is how massive the planet is, and you can see our planets labeled there. They're not falling in the same realm as other solar systems. So the question is, if our solar system is really different, is that what makes it special and the reason it has life? So how do we go back and figure out if we had life in our, or how our solar system formed, since it's already happened? Well, we have to go back in time, and the best way to do that is to do some archaeology. We have to look at the leftover bits and pieces from the process of building a planet. You know, our planetary system started as a cloud of gas and dust that gradually collapsed. The dust grains got together, got bigger and bigger, until you have these remnant, what we would call planetesimals, that are kilometer scale, and they'll eventually form into planets. Some don't quite make it. They get thrown out into outer regions of the solar system, crash into the sun. It's the leftovers that we want to look at today, and those are comets and asteroids in the asteroid belt. So what does it mean to be habitable? Well, we need the right ingredients for life, and for us that means organics and water. Problem is, our solar system is actually quite dry. You know, Mercury, Venus, the Moon, Mars don't seem to have much water. Earth looks like a nice oasis in space, but it doesn't actually have much water. And that's actually a good thing, because people that talk about the formation of life say, you really need to have dry land. You need to have dry land with just occasional water. We're getting all sorts of organic compounds falling onto Earth from space, and you need a way to concentrate those compounds in a way that they can start to build up really complex molecules. So if you don't have dry land, you may never start life. You've probably seen some science fiction movies with a beautiful image like the one in the upper right, a water world. That probably wouldn't be very good even if you started life, because on a water world with no dry land, you have no means of removing and weathering the rocks to get phosphorus, potassium, things that you need for life. If you have way too much water, say 50 oceans of water, the pressure at the base of the ocean is so intense, you stop all of the weathering and cycling, carbon dioxide recycling in the atmosphere, so you wouldn't have a very good climate. So it's not only we need water, we need just the right amount. So how did it get here? Well, I like to start with a timeline. What do we actually know? Well, we know a couple of things. We know the age at which the solar system started, 4.5 billion years ago. And we know that from images from meteorites. We can actually measure the very first solids that froze out in our early cloud of gas and dust. We measure those very precisely to 4.5 billion years. Also comet particles shown from the Stardust Comet Dust mission. On the other end, about 200 to 300 million years later, we know that we had oceans. We've got a couple of pieces of evidence for this. Both the granites, the oldest granites we see on Earth, these need to form with multiple cycles of volcanic eruption in ocean water. And likewise, some tiny crystals called zircons in Australia also indicate that they erupted in water, and they're all dated to about 4.3 billion years. So that's the when. What are the possibilities? One possibility is, well, Earth formed really close to the sun where it was warm and there was a lot of gas in the nebula. Maybe that gas just stuck to the little tiny dust grains and it got trapped as it built up bigger and bigger pieces. That's possible, but many people think that as things crash together at higher and higher speeds, you won't keep the water. Another idea is once the Earth has gotten pretty big, it went through periods where the whole surface was molten. If there was hydrogen gas in our atmosphere, chemical reactions could make water on the surface of Earth. But we don't know if we had hydrogen in our atmosphere or if it was at the same time when we had a molten surface. And finally, what if there's icy things from the outer solar system that ran into the Earth that could have brought our water? And in fact, we see evidence of that with craters on the Moon and craters on everything in the solar system. So how are we going to tell these different ideas apart? Well, it turns out that in the 1970s and 80s, people had understood that Earth's ocean water chemistry had an excess of deuterium. It was a heavy form of water, and it was much higher than expected from just the gases in our neighborhood, the things that would have formed the solar system. And so they were puzzled by this until the Europeans sent a spacecraft to Comet Halley. The spacecraft flew through the tail and actually measured the composition of the water, and it was heavy also. It's called the D to H ratio, deuterium to hydrogen. And in fact, the water in Comet Halley was about twice as elevated as that in Earth's oceans. People got excited. This is the smoking gun. This is where we get our water. Comets crashed into the Earth early on. Another comet was measured from the ground, seems to fit the story. But if all comets are this high, it doesn't really match Earth's oceans. Plus, at the same time, people were measuring meteorites collected on Earth, and they have a wide range of D to H in the water that's locked up in their minerals. So let's examine, this is our framework for figuring out where water came from. Let's examine it in a little bit of detail. And let's start with, how do we actually know what the starting value for the solar system was? Well, in the 1970s and 80s, the chemists went out and they've done all sorts of calculations, and they said it is really easy to make molecules with deuterium at really low temperatures. That's preferred. So everybody understood the process. But once people started to make models of how you build a solar system, it started to get really complicated. And what you see in the beautiful, colorful diagram in the middle, this is a model as a function of distance from the sun. The different colors show you the variation in the amount of the heavy water, and it's not uniform. So the part that's troubling here is, how can anyone claim there is one value for the amount of deuterium to hydrogen in the solar system? You can't. And in fact, this will change with time. So really what we can say is we have no clue what the DDH value was for the early solar system. What about comets? How do you measure those? We can't send a spacecraft to everybody. Fortunately, we don't have to. We can use the telescopes on Mauna Kea, but it's a hard measurement, and so it's only been done for about a dozen. And so the figure in the middle shows all the red points is the D to H, and Earth ocean is at the bottom, the black horizontal line. Gee, they're not matching at all. So finally, we measured a different type of comet that formed farther from the sun. Those are the two pink ones. And we were surprised. It formed colder. Everybody said the physics and the chemistry says it should be higher. What goes wrong? So people redid their models. We fixed the bug in the models. Now they waited for the very next comet to be observed, which was with the spacecraft from the European Space Agency, and it was really high, the orange point. So everyone says, we have no idea what the D to H in comets is. We have no idea how to make the predictions. So we can pretty much confidently put a question mark there. You probably see where I'm going there. Meteorites. We've got thousands of these. How do you measure D to H in a meteorite? Well, the lower picture on your right here is the ion probe at the University of Hawaii. You take these tiny minerals and you can make very precise measurements. And what it showed in the chart in the middle, the histogram, that the meteorites indeed matched the Earth. So why are we going to all this trouble? Aren't we just done? Well, in fact, meteorites don't match the Earth with very many other chemical species. So, can meteorites really be the things that were the only deliverer of water? And the answer is probably no. So we'll put a big question mark there. Well, what about the left? Surely we understand D to H of oceans. A lot of water, you can go out and measure it, not a hard task to do. But wait a minute, how much water do we have on Earth, and is this the right place to measure it? So the chair of the Oceanography Department of UH, 2007, did a huge review paper. And what it's showing here, at the top row, you can see how much water is in the oceans and atmosphere. You can estimate the volume, 1.3 oceans worth. As you go deeper and deeper into the Earth, we can't measure it. It's theoretical, lab experiments. You can see some people measured low values, some measured high. And there's a difference between 1.5 or 11 oceans of water. And he thinks it's probably 3 to 4 oceans. So there's more water inside than on the surface. So we weren't even measuring water in the right place. So after a meeting I went to in Iceland, we did a geological field trip, and we saw the steam coming out of the ground, and the geologist said, it's okay, it's cool, it's water, go right up to it if you want, it's primordial water. My little kindergarten light bulb went off. Primordial water, that's what we should be measuring. I was so excited, I changed my flights. I went to the University of Iceland, and he said, well, she's wrong. It's rainwater. Goes down, gets heated up, comes out of steam, and I was very disappointed. He said, but wait, we have seen primordial gases coming from the Earth. And I said, have you ever measured D to H? And she said, no. It would require a state-of-the-art ion microprobe, and I said, UH just got one. And so that led me into geological forays. I went with a volcanologist to sample rocks from Iceland, because the idea is special places like Hawaii, Iceland, various other places on Earth, primitive material does come up to the surface. So we were out in the field, I took that picture and I said, I'm sorry, but all the rocks look exactly the same to me. How do I know which one's important to pick? And he said, that's why you have me along. I said, well, you're not being a very good teacher. He eventually showed me how to pick it. We had a postdoc do the measurements, and it turns out that the water from the deep Earth is very different from the ocean water. So I'm afraid we're going to have to put a question mark over there. We have no clue what the D to H of Earth is. So this is our framework for figuring out everything. So just to pause here, let's do some takeaway numbers. I think probably what's going to be important is the journey. It may not be so much the answer, but the journey is going to be very important. And I think water may have come from many sources. But don't film this or don't write this down. I will show you what fraction we think comes from each source. As of today, it's not published, so I hesitate to share this with you. But there you go. That's how much comes from asteroids, the gas and nebula, chemical reactions. And I really apologize for so many significant figures. I was just a bit sloppy there. Again, please don't tweet that out. So now what? Now we've got this framework. We're doing all this high-pressure science. Now what do? You kind of feel a little bit like this. Well, it's a complicated process. You've got chemistry that's a function of temperature. You're building planets. Things are moving around. But in fact, within the last decade, there was a very interesting paper that came from a field that I wasn't expecting. And this was people studying iron meteorites. And what they found was a set of iron meteorites. They're all primitive. They were kind of expected to form in the same place. They have very different chemistry. It's not just a scatter diagram. They plot in very distinct regions, but they all formed at the same time. And why is this so surprising? Well, in the early solar system, the dust tends to migrate towards the star. It drifts inwards unless you have a planet that's growing that forms a gap, and then it gets trapped. So what these scientists thought was happening, we started out uniform, everything's drifting in, then Jupiter starts to grow in the second step up, and a supernova goes off nearby and contaminates the outer solar system, but not the inner solar system. So now we have two reservoirs, Jupiter gets bigger and bigger, and finally, when it's up to 50 times the mass of the Earth, now it's big enough, things can get across the gap, it's throwing things in gravitationally. So either Earth got some of its water where it formed close to the sun in the bright orange region, or Jupiter threw some icy things in from outwards. So how are we going to prove this or test it? Well, I think this is where the engineering solution comes in. We need to look at the things that got tossed inwards. Anything Jupiter threw in, hit all of the rocky planets, and got trapped in the asteroid belt where it sits today. And so all we need to do is find something in the asteroid belt with water. These have been discovered. They're called main belt comets. They have tails like comets. And I think what we need to do is send a spacecraft there and measure the D to H and other isotopic signatures. But if we want to get really fancy, I think what we really ought to do is do something like the recent OSIRIS-REx mission and send a spacecraft and grab a sample and bring it back to Earth. And I think this will be the engineering solution that helps us understand where water came from. So I think it's going to be a really exciting journey. It's going to be an interdisciplinary journey. And I tell you, as an astronomer, I've had a lot of fun holding a rock hammer. I wasn't finding it so much fun looking through the microscope, separating grains of sand, but I've enjoyed the journey. I think it's exciting to come, and I'm looking forward to putting together space missions because I think the answer is really fundamental. It'll tell us a little bit of the pathway to whether or not we're alone in the universe, because if it requires a special technique to make our solar system that's habitable, does that need to happen elsewhere? So thank you very much.
Engineers and architects of Hawaii welcome your comments on this program and any of our recent programs. We encourage your direct participation in this community outreach, so please email us your comments and ideas at eahawaii@gmail.com.